get too close to a black hole, and time doesn't just slow down, it stops, and then it moves backward. Here's the math that proves it, and why it's way worse than you think. Before we break your brain with relativity, quick thing. If you end up enjoying this existential crisis, subscribe. We're doing a whole series on things in space that shouldn't be possible, but very much are. Alright, let's ruin time for you. First, we need to understand what time actually is, because it's not what you think. You think of time as this constant thing. Tick, tock, tick, tock. A second is a second, an hour is an hour, no matter where you are, right? Wrong. Time isn't a constant, it's a dimension, the fourth dimension. And just like you can stretch a rubber band in the 3 dimensions you're familiar with, you can stretch time itself. Einstein figured this out in 1915. He called it general relativity, and here's the core idea in one sentence. Gravity isn't a force, it's curved space-time. Mass, like stars, planets, black holes, these things don't just exist in space, they warp space. And when you warp space, you warp time too. They're the same thing, space-time. Think of space-time like a trampoline. Put a bowling ball in the center, the fabric sinks, that's gravity. But here's what textbooks don't emphasize. When that fabric stretches in space, it also stretches in time. So the closer you get to something massive, the more space-time warps, and the more time itself slows down. This isn't theory, we've measured it. GPS satellites orbit Earth at 20,000 kilometers up. Up there, they're further from Earth's gravity, so time moves faster for them. About 38 microseconds per day faster than clocks on Earth's surface. Doesn't sound like much, but if we didn't account for this in GPS calculations, your navigation would be off by kilometers within a single day. Time is flexible. Gravity stretches it, and nothing has more gravity than a black hole. So let's see what happens when we take this to the absolute extreme. Imagine you're in a spacecraft approaching a black hole. You're not suicidal, you're keeping a safe distance, but your friend, for science, decides to get closer. You watch through your telescope as they descend, and something strange starts happening. They're slowing down, not their engines, they are. Their movements become sluggish. You radio them, everything okay? Their response comes back slow, stretched. Every word takes longer than it should. From your perspective, they're being slowed down by time dilation. The closer they get to the event horizon, the more extreme it gets. The event horizon, that's the boundary of the black hole, the point where gravity becomes so strong that even light can't escape. And that's where time dilation goes infinite. As your friend approaches the event horizon, from your safe distance, you see them slow down more and more and more until they freeze completely. 1 second from crossing the horizon, and to you, they never move again, ever. They're not dead, they're not stopped, they're just stuck in time. From your reference frame, they will hover at the edge of that event horizon for eternity. You could wait 1 trillion years, they'd still be there, frozen. That's your perspective, but here's the thing. From their perspective, nothing unusual happens at all. Your friend crosses the event horizon smoothly. Their clock ticks normally. They check their watch. Seems fine. They look back up toward where you were, and the universe is moving at incredible speed. Stars are being born and dying in seconds. Galaxies are colliding. Everything outside is in fast forward because time is moving so slowly for them that everything else seems fast. If they could watch long enough, which they can't, they have about 1 second to the singularity, they'd see the end of the universe. This is the psychological horror of relativity. From outside, your friend is frozen forever. From inside, your friend sees the heat death of the universe in fast forward. Both are true, simultaneously. But it gets so much worse. Now, you've probably heard of spaghettification. That's the fun term for what happens to your body near a black hole. Your feet are closer to the singularity than your head, so they experience stronger gravity. But here's what's less discussed. You don't just get spaghettified in space, you get spaghettified in time. Your feet are experiencing stronger time dilation than your head, so your feet are aging slower than your head. By the time you hit the singularity, your head could be seconds older than your feet. You're not just being torn apart in space, you're being torn apart in time. Different parts of your body existing at different moments. And then you hit the singularity and everything becomes a single point, and you stop existing in any meaningful way. But let's stay outside the event horizon for now, because even out here, things get philosophically disturbing. Alright, so your friend crosses the event horizon. From their perspective, it's smooth. No barrier, no wall, just one moment they're outside, next moment they're inside. But something has fundamentally changed, not just in space-time, but in the structure of causality. Outside the event horizon, time flows in one direction, forward. You can move freely in space, left, right, forward, backward, but time, you're locked into moving forward through it. Inside the event horizon, these roles swap. Space becomes the thing you can't control, and time becomes the dimension you can move through. Every direction you try to move in space, every direction you can point, every direction you can travel leads to the singularity. Up, singularity. Down, singularity. Forward, backward, left, right. Singularity, 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 singularity. It's not that the gravity is pulling you, it's that the future is pulling you. Because inside the event horizon, the singularity isn't a place in space, it's a moment in time. Your future. Think about that. Right now, outside a black hole, you can't avoid tomorrow. Tomorrow is coming whether you like it or not. You can't escape time. Inside a black hole, the singularity is tomorrow. And just like you can't stop tomorrow from arriving, you can't stop yourself from hitting the singularity. The black hole isn't eating you in space, it's eating you in time. This is what physicists mean when they say the singularity is in your future, not ahead of you. It's not in front of you, it's in your when, not your where. And this is where physics breaks, because we don't know what happens at the singularity. Our equations stop working. General relativity says density becomes infinite, volume becomes zero, which is physics speak for we have no idea. Does time end? Does it loop? Does it fragment? Do you tunnel to another universe? We don't know. But here's what we do know. Once you're inside, you're not coming back. Not because you can't escape the gravity, because you can't escape time. So black holes eat time. They trap it inside event horizons. They compress everything into singularities where physics breaks, which raises a disturbing question. Where does the information go? In physics, information can't be destroyed. That's a fundamental law. If I burn a book, the information isn't gone. It's in the smoke particles, the ash, the heat radiation, scrambled beyond recognition, but theoretically recoverable. But black holes seem to destroy information completely. You fall in, you hit the singularity, and nothing comes out. The information about your atoms, your structure, your quantum states, it's just gone. This bothered Stephen Hawking so much that he spent decades trying to solve it, and in 1974, he discovered something that made it worse: Hawking radiation. Through quantum mechanics, black holes actually evaporate, slowly, very slowly. Particle-antiparticle pairs form at the event horizon. One falls in, one escapes. Over trillions of years, this radiation causes the black hole to lose mass. Eventually, it disappears completely. Which means black holes aren't eternal, they're temporary prisons. And when they finally evaporate, where did all that information go? The information about every star, every planet, every person that ever fell in over billions of years. Is it in the radiation? Is it encoded in some way? Is it escaped into other dimensions or universes? We still don't know. But here's the unsettling part for our time discussion. Remember our friend who fell in? From the outside universe's perspective, they're frozen at the event horizon forever, right? But the black hole evaporates. Eventually, it's gone. So what happens to the frozen image of our friend? Do they suddenly fall in when the black hole disappears? Do they get released? Do they never fall in at all from our timeline? This is called the firewall paradox, and we don't have an answer. What we do know is this: black holes trap time itself. They compress it, stretch it, break it, and maybe eventually release it in ways we don't understand. They're not just holes in space, they're holes in time, and everything that falls in, every moment, every second, every now that crosses that horizon is locked away from the universe's flow of causality. Black holes are eating time, and unlike space, you can't get time back. There's something profound about this. We spend our lives fighting time, trying to save it, manage it, make the most of it. We say time flies and time heals and time is money. But time isn't something we have, it's something we move through, a dimension,